Then welcome to Cryptography on Hardware, in the third session. Today, I would like to give you some information about the FPGAs in general, and then we focus on the board that you will get today, Cmod A7. And then we have a sample project for this, and then we work with the details of the board and check how we can make it running and how to configure it, how to make a simple program or simple design on it, and then check it. A bit of introduction of the history, what happens that we have at the moment FPGAs. The first concept for programmable hardware was initiated more than 60 years ago, and that was programmable RAM, or read-only memory. Means that you have a chip that you can program, but then you can realize any function that you want. How did it work? RAM or read-only memory, you have actually a lookup table, and you give an address, and the data is actually here, at the address 0, address 1 till, for example, 2 to the n-1 if you have n-bit address, and the data, for example, is m-bit, and this m-bit data comes out. And then suppose that this is just a lookup table, and if you are able to configure this chip, as a lookup table, then this n-bit address and m-bit data are available as the primary input and primary output on the chip, then you can realize any function that you want. Of course, as long as the number of inputs that you want to give the circuit is not larger than the number of the address bits. But this is just a combinational circuit. Then you cannot build any flip-flop or any register for this. This is just a function that you can build, an arbitrary function because it's a lookup table, but without any register. But this was the, let's say, first step. Then the next idea was PLA, or programmable logic array, if you have heard. That actually it gives you an opportunity to build a more complex circuit, not just like a lookup table, and it has as you can see here, there are some places for the AND gate and the OR gate, and the interconnection between them are completely programmable. We will see more details about that. And then afterwards, it was supposed that this is too complicated, and many configurations like do something else, which is called programmable and generic array logic, which is called PAL or GAL. And it means that the AND part is configurable, but not the OR part. The OR part is completely fixed. We will see that. And the next version of this, which was a combination of a few PAL and PLA inside a chip, was CPLD, which is called Complex Programmable Logic Devices. And they are, I wouldn't say that they are produced at the moment, but if still you can get some chips like the CPLD in the market. I mean, outdated and not produced anymore, but you still can get something from the stack. And then the next version or next generation was really the FPGAs, or field programmable gate arrays. And a large number of flexible logic elements were involved and included to build many functionalities or realize many functionalities. We will see this. What is the PLA? First of all, it's working based on sum of product, or SOP. I hope you remember SOP, or sum of products. For example, you had 3 inputs, X, Y, and Z, and the output is, for example, T. And then you say T equals X, Y bar, and then plus X, Y, Z plus X, for example, Z. This is a sum of product, means that here you have AND gate, and here you have OR gates. Means that some terms that they are AND together, and then the terms are connected together via an OR. Yeah, and then not all the inputs are connected. If you have observed here, it's here XY, and not ZX is not available here and not involved, not necessarily. And then how to realize this? This was the construction that there is an AND gate here with some inputs connected to some of these gates, some of these inputs, X1, X2, X3, and also the invert of them. And there were some fuses here that you could burn. That means that they are originally, when they come from the market, from the company, they were connected, but you could kill or burn these fuses, and then this connection was gone. And of course, this was designed like this. If they are not connected to anywhere, then they should be connected to the VDD. Yeah? Otherwise, if the input of the AND gate is connected to 0, the output is always 0. Yeah? How? Yeah? If it's an AND gate, yeah, there's this input. There are 3 inputs with the fuse. And this is connected by a resistor to the VDD. No? Means that if this fuse is not there, this is connected with a resistor, a small resistor to the VDD, and then it receives 1. Otherwise, first of all, you cannot leave any connection of the digital circuit floating. And if you do not also connect it to the VDD, it will be connected to, for example, ground, then the output of the AND will be always 0 if you kill in a single fuse. Then the output of these AND gates are going to the OR plane here, which is also configurable. And then by this, you actually build the terms, the terms of the product terms. So maybe it says sum of the products. By this, you define which term you want to OR together. It means that here by this, you have 3 inputs and 2 output functions you can build. But of course, it will not allow you to produce any function that you want, because it depends on the number of these AND gates which are available here, whether they allow all the combination between X1, X2, and X3. And then afterwards, the PAL was said, okay, this is too complicated. Let's fix the OR part, because it's pretty clear that what you want to do, and you can also realize some other functionalities without having the OR completely flexible. It means that here you have the OR gate completely fixed, and then the AND gate will be implemented by this, still configurable. And then this notation is like this. If you have a mark here, means that this line is connected to X1. It means that when it comes from the company, all of them are connected, and then you kill some fuses to disconnect them. And then you may say, if the OR gate has 3 inputs, for example, but I have just only 2 elements in my, or 2 terms in my sum of products, how I can implement this, because it has 3 inputs, then of course the third input should not be connected to anywhere. It means that the output of this AND gate should be always 0. Then you can realize it. Or you can say both X1 and X invert are connected to that AND gate, then definitely the output of that AND gate is 0. Now, what is a CPLD? As I said, is a collection of circuit blocks like the PLA and PAL, and they are also connected to some internally connected blocks, and then they go through an I/O block to communicate to outside. Here there is a block, PAL block, for example, that you can configure. You can realize the function. And then some interconnections that you usually, these are not configurable most of the time. Then by this, by configuring these blocks, you can say how they should work. But there are some connections here that you can use and connect this output of this to input of the other one, and so on. And then at the end, when you build your circuit here, you have to give some inputs from the outside and some outputs to the outside. And they are called I/O blocks, because not every internal wire will be controlled from the outside. And some of them are configurable, some of them are not. And then, of course, this cannot be done manually. There were tools. The companies who produced CPLD also delivered some tools and some programs to realize this functionality. It means that you write again your program like VHDL or Verilog. I mean, at that time, I don't know really whether it was possible or supported. But anyway, by some description, you represent your function that you want to realize, and then the tool was turned to the configuration of particular CPLD to realize this functionality. Then FPGAs, the first version by Xilinx was introduced in 1985, which was XC2064. This was the first version. And originally, actually, it was offered or produced for telecommunications and also switching technologies. You know? Means that it was not for general purpose things. I mean, there was for something that you need flexibility and you also need very high performance. Means that flexibility, of course, was possible through microcontrollers, but it was not high performant. And then that was the first, let's say, application of the FPGAs. And then it went to many other areas with high requirements for speed and efficiency. And then 1995 was a start of developing and considering cryptographic applications inside the FPGAs. It means that the companies or FPGA vendors produce themselves something inside the FPGA to support some functionalities. I mean, what we are doing in this lecture, we are actually using the FPGA itself just to realize the functionality of a cryptographic functionality. It doesn't mean that we are using some cryptographic facilities of the FPGAs. No? But for example, AES, some modules of the AES are available in some new Xilinx and other FPGAs. And then we are not using them at the moment. No, we are not going to use them. We are using FPGAs just to realize every functionality, and the case study for us is cryptographic primitives. The current FPGAs, the family of the Xilinx, which are called Ultra Scale and Ultra Scale Plus, they offer a huge number of resources. For example, more than 1 million logic elements, that we will see more details, and some dedicated memory inside more than 100 megabits of data, and many other features for DSP, for example, processors, and even some ARM core as a CPU is inside, and USB functionalities, LAN support, VGA or HDMI support, and many other things. And of course, depending on the family and depending on the part number that you get. Of course, if you have more features, then it becomes larger and of course more expensive. If you want to compare FPGAs with CPLDs, FPGAs do not consist of any AND and OR gates. You will see how the logic is implemented by FPGA. And the main components of the FPGAs are actually CLBs, which is called configurable logic block. Now, and inside the CLB, I mean, every CLB consists of some other elements that you will see, like the lookup tables and the flip-flops. But then usually FPGA consists of several CLBs, and then the configuration of the CLBs we can do, and also the interconnection between the CLBs we can also do. And if you want to simplify the things, I mean, FPGAs consist of CLBs and programmable interconnections. This is exactly what I just explained. Yeah, the CLBs will be configurable, and configurations or connection between them is also configurable and programmable. As I said, I mean, we have a lot of CLBs inside the FPGA. If you want to have a plan or floor plan of the FPGA, here you see here configurable logic block CLBs, and every of these tiles, the blue ones, is a CLB. And then between the CLBs, we have these red ones, which are block memory or block RAMs that we will learn later how they work. And then some I/O blocks, I mean that at the corner, there are some I/O blocks, means that you want to communicate as primary input and primary output with the circuit. That they are also configurable because you have a single line here, you want to route it to output, then this should go and pass through some programmable connections, which are called switch boxes. And these switch boxes are not just for the intermediate values or intermediate signals to be connected to the I/O blocks, also to the block memory or block RAMs, and also to clock management units This is called DCM in old, digital clock management. And some clock buffers and even some multipliers and digital signal processing units inside. Yeah, I mean every FPGA, as I said, is different, but this is just a sample. Yeah, means that if you look at another FPGA, it will not be necessarily like this. It might be actually not symmetric at all. Yeah. Now, what is inside the CLB? The CLB in the Xilinx FPGAs in 7 series, they consist of 2 slices. We will see what the slices are. Yeah, 2 slices and 1 switch matrix, which is connected to CLB. And then it controls which inputs will be connected to which inputs of the slice. And then keep in your mind that in the Xilinx FPGAs, they also cover carry look-ahead adder. Yeah, that you see here, carry in and they carry out, and then it lets you implement the adders pretty fast. And then Xilinx 7 series, one of the families is called Artix 7, and this is XC7A35T or 35T is exactly what is available on the Cmod board that you actually will get. Yeah, the super small chip here with the sticker. Yeah, it's written 35T. This is the FPGA, and it consists of 3600 slice L and 1800 slice M. But what are these slice L and slice M? This might be too small for you to see, but I'm sorry for that. You may search and find it and enlarge this screen, this photo. This is a slice L. Here, let me explain like this, that the slice L, these blocks that you see here, they are the lookup tables. Yeah? They are the lookup tables exactly similar to RAM, read-only memory that I explained. Yeah, that you cannot write on this, you just read from them, but you can configure it. Yeah? The configuration of the FPGA, for example, configures these lookup tables. And then 6 inputs, 2 outputs. We will deal with this in more detail later. And 4 of them here, you see there are some inputs for 6 input, 6 input, and 6 input, completely individually and different. And then 2 outputs are coming here, and here there is a register, yeah, and clock enable, blah, blah. And here another register and a couple of multiplexers and so on to define and configurable to say, okay, the output of the LUT goes here at the output because it's the output of the LUT, or this part, whether the output of this goes outside or the output goes to the register and the output of the register goes outside. And here you see here D is the output, here DQ is the output, here C is for this lookup table, and CQ is the output coming from this register. There are many things which are configurable here, and as I said, we are not able to manually build something. Yeah, of course it's possible if you want to change the configuration by yourself and build something by yourself, but everything will be handled by the Vivado, for example, yeah, the program of the FPGA vendor. This is a slice L, which is complicated. A slice M is even more complicated, and it has some other features. For example, one of the features that you see here, that the lookup table doesn't have only the input, 6-bit input and 2 output bits. There is a clock, there is a write, enable, and so on. Now, what is it? What does it mean? Yeah, this is writable, means that you can change the content of the lookup table during the runtime of the FPGA, not only during the configuration. But you cannot change every value that you want. Yeah, this is kind of a shift register, that you put a value, you clock, then, for example, some bits are shifted and the new values will be loaded and so on. Yeah? But you can entirely change the content of the lookup table of the slice M. But of course, it takes a couple of clock cycles. And you cannot change the entire configuration of a lookup table in one clock cycle. It takes some time, but it's possible to reconfigure this completely. And some other functionalities you can see here. For example, it's a flip-flop or latch. You can select init 1, init 0, means that after the power up, whether the value of the flip-flop is 0 or 1. It's also written SRHI is set reset with high or set reset with low. Means the active low, active high, set or reset. And there is a clock enable clock and the D as the input and the SR as the set or reset. And keep in your mind that you cannot have both set and reset in one flip-flop of the FPGA. Either there is a FPGA, there is a flip-flop with set or there is a flip-flop with reset. And usually this reset type, synchronous and asynchronous, is completely the same for the entire flip-flops of the slice. You cannot, for example, say this is synchronous reset, this is asynchronous reset, and so on. Of course, every slice is different to the other. You can change the configuration of the other slice. Then if you have one flip-flop with synchronous reset and another one with the asynchronous reset, they cannot be in one slice. But you should not care about this. I mean, this will be again done, handled by Vivado, the FPGA vendor tool. Okay. Now, FPGA elements, loots, I explained this slightly, but we go to more details. The loots or lookup tables are the most used elements of the FPGA. And as I said, they are similar to RAM, and they can be also used as shift register, what I explained. Here in the FPGA that you have more than 20,000 lookup tables are available. Then any combinational circuit that you want to implement is, of course, possible to use to be implemented using those many lookup tables. How this works is an example. The loot 4x1. Then you have the content of the value, or the value of the content of the registers, 0 to 15. The values are single bit, means that 16 single bit values, which are stored here. And this is the configurable part. And this is the multiplexer tree. I0, select whether 0 or 1 goes here. I mean, the value which is stored here or the value which is stored here passes through the first multiplexer. And all of the multiplexers which are here, they are controlled by I0. And I1 select two neighboring outputs of the multiplex first, the last multiplexer stage, and I2 the same and I3 the same at the end, and you get one output. And this is 4-bit input and 1-bit output LUT, and then by this you can realize any function, any combinational function with 4 inputs, at most 4 inputs. In Xilinx 7 series, the lookup tables are not 4 to 1. Of course, you can ignore 2 inputs and then realize a 4 to 1 input, 4 to 1 LUT. But the LUTs are actually like this. Either you have 5x2 or 6x1 LUT. There are 2 LUTs here in every LUT that you have since 6 inputs with 64-bit configuration. And there is a multiplexer tree from I0 to I4, means that's 5 bits to here. The same 5 bit is connected to this guy. And the last one here, if you consider here, this output goes here, and here 01 is actually an output of a here 6 to 1 LUT. Means that you can easily implement 6 to 1. But one of the outputs here is also given outside. Means that you can completely ignore this I5 and set it in a way that this output is coming out and this is completely ignored. Then you have 2 completely individual and independent 5 to 1 lookup table. Then we call it 5 to 2. They are individual, the configuration are individual, but the inputs are shared. Means that if you want to change the input of this, the input of this is also changed. If you look at the document of Xilinx, you will see here, it's called 6 to 2, sorry. It's called 6 to 2 lookup table. But they are not 6 to 2. I mean, you cannot realize any 6 to 2 function here, because it's one of them is always connected to here, and for the 6 to 2, if it's completely individual, then you need actually okay, this is gone. Then if you want to have a 6 to 2 lookup table, then you need more logic here, yeah, to exactly give you 2 output bits, individually 2 output bits, yeah, and then more configuration you need for that. Good. Now, an example, you want to realize an 8-bit to 8-bit function by lookup table. Then how do you do that? Of course, again, if you write an 8-bit to 8-bit function, the Vivado will do it for you. But how this will be done? Generally, you can realize arbitrary 8 to 8-bit function by some loots, right? I mean, 8 times 8 loots are required. It means 8 by 8 loots, or 8 times 8 by 1 loot you need. But we do not have 8 by 1 loot in the FPGAs. Then we have to use 6 by 1 loots. And then the question is, how many of these 6 by 1 loots are needed? Yeah. Here you can see that you need 4 instances of 6 by 1 loot to realize the 8 by 1 loot. How does it work? Here, by this 6 by 1, you have 2 to the 6 possible values to store, but you need 2 to the 8. Yeah, 2 to the 8, and then 2 to the 8 divided by 2 to the 6 is 2 to the 2. Then 4 loots definitely at least you need to store the content of an 8-bit to 1-bit lookup table. And then you get 4 output bits. And again, you need to realize a multiplexer by loot, yeah, to select one of these outputs to the out, of course, with 2 input signals. And then in total, you need 5 loots, or 5 6 to 1 loots to realize an 8 by 1 loot. Yeah? And then what we said we need 8 by 8 function, then you need 8 of these constructions. Yeah, and then it would be 40 loots in total that you need on these Xilinx FPGAs. But of course, as I said, this is just to implement an arbitrary function. If you give the definition of this function to Vivado, it will try to minimize this and may optimize it and use less number of loots to realize that 8-bit to 8-bit function that you want. But what is this? Is maximum you need 40 loots, yeah, to realize an arbitrary 8-bit by 8-bit function. Now, another option or another component which is available in the FPGAs is called BRAM or block RAM. It's a dedicated memory. For example, in many of the Xilinx FPGAs, you have 18 or 36 kilobit of block RAMs. I mean, you can select usually. Yeah, I mean, of course, it's like this: that 2 18 will be cascaded together to build this, or sometime both of them are available. Both cases are available in one FPGA. If you can see it here, there are the primary input and primary outputs, and this is called data in address, data in parity address, data write address, read address, and so on. And it's like this. It's not like a lookup table, but of course it's a lookup table actually, but it's not like loot. The big difference between the block RAM and the loot is that, of course, the block RAM is larger, but at the same time, you need actually a clock for block RAM. The lookup table loot doesn't have any clock. It's a fully combinational. But block RAM has a clock, means that it reads really from the memory. You give the address, and given a positive edge of the clock, it reads the value from the memory and puts it in the output register. And what is interesting, it has 2 completely individually and independent, 2 individual and independent ports. Means that you can read from the same content of the memory from 2 different ports, and it's called true dual port. And of course, you can read at the same time from different part of the memory, 2 different addresses from the same content. But of course, you cannot write easily at the same time in the same addresses. I mean, different addresses, you may be able to write, but writing at the same address leads to collision, and you cannot also predict at the end what should be the value which is written in the register. Then by this, block RAM can be also cascaded. Much larger block RAMs you can build, and it's also supported by Vivado, for example. You can say, I want that large RAM, and then it builds by itself already some block RAMs and cascade them together to reach exactly what you want. Of course, if the resources which are available on the target FPGA are enough for that. It has also some functionality which is called parity check, but it doesn't check actually. It's just extra memory that you can check by yourself. I mean, you can add this by yourself. It's just extra part of the memory. You may think of, why 18 instead of 16? It's this weird 18 kilobit. It's exactly because of the parity which is added to this functionality. As I said, it's the parity. This is not calculated. This is something that you give, and you can also check by yourself in your design. And what is also important, each port has its own clock. It means it's completely individually and independently you can read and write, with their own clock, clock A and clock B for the port A, for the port B. And it's also configurable. I forgot to tell you that it's also configurable. You can also configure how long should be the value that you want to read and write. Not during the runtime, during the configuration. We can say, for example, I want to read and write every time just 2-bit values. My words are 2 bits or they are 16 bits. Of course, not every value is possible. This is not arbitrary. There is a list that you select, either 1-bit, 2-bit, 4-bit, 8-bit, 16-bit, 32-bit, and so on. Good. Now, again, a bit of the history about the FPGAs of Xilinx. In Virtex 2 Pro architecture announced in 2001, that was I mean, if you consider the current technology, that's a super old, 130 nanometer, and that was super interesting at that time, but it's now considered super old and super large design. But it has many features which are actually already, of course, as I said, the chip is outdated, it's not produced anymore, but it has many features which are actually interesting either at the moment. For example, it showed and announced high performance true dual port RAM that I just explained, which were not available before. And then select I/O Ultra technology for some functionality that you can select during the runtime, the direction of the port. Some advanced logic FPGAs, for example, around 100 kilo of logic cells, DSP functionalities, many other things, PowerPC processor inside that you can realize, and DCM clock managements that I don't know whether you are aware of some modules that you can add to hardware designs to, for example, slow down the clock or even multiply the clock. For example, PLL, if you have heard. Then, for example, you provide the device with 10 megahertz, but then with the PLL you can multiply it by 10 and then get 100 megahertz inside the chip, because providing the high clock frequency from the I/O port is actually not possible. I mean, even if your circuit is available, is able to work with, for example, 400 megahertz, you can never provide 400 megahertz clock from the outside. You have to provide a slower one, for example, 100 megahertz, 50 megahertz. And it goes inside, and then inside will be multiplied by a factor. Because the I/O ports actually have a limit. The I/O ports cannot deliver, for example, 500, 400 megahertz changes. And for that reason, I mean, the I/O voltage VDD of the I/O is higher than the VDD of the internal of the core. I mean, the core, for example, works with 1 volt, but the I/O works with minimum 1.8 volts, or 2.5 volts. Then afterwards, after 2 years, we had the Virtex 4 architecture, again 90 nanometer technology, and also with the Spartan 3 You see many more things like the smart RAM, rocket I/O multi-gigabit transceivers, advanced CLBs. I mean, similar to what you just have seen for 7 series, similar, not exactly the same. For example, the 1 gigabit per second select I/O, Power PC inside, and many other features that you can never believe that what they could put inside a chip and also configurable. And you see 20 years ago. And in 2006, Virtex 5 architecture with many new functionalities, real 6-loop fabric, as you saw just now, and some built-in ADC analog to digital converters, and again, next generation Power PC embedded processor. Yeah, I mean, the Power PC is similar to ARM right now. I mean, that time it was Power PC as the embedded processor, and many other features. Like, for example, you see here 10 or 100 or 1,000 megabit per second Ethernet functionalities and the features and so on. In the newer technologies, afterwards, we had Series 6 or 6 series, Virtex 6, Spartan 6, and the other families, and the 7 series, which are at the moment produced, partially, Virtex 7, Spartan 7, Arctic 7, and Kintex 7. What you have in the Cmod A7 is one of the Arctic 7. Yeah? And they are different families, and inside every family there are, I don't know, 20, 30 different also FPGAs, and inside each of them again a few different packaging types. Yeah? Then you can imagine how many different chips they are producing. Yeah? And then in the last families, which are more expensive and more functionality, also Ultra Scale and Ultra Scale Plus, we have Virtex, Kintex, Arctics. Yeah, Spartan doesn't exist in Ultra Scale anymore, but we have Zinc. Zinc devices are actually a combination of the ARM CPU and an FPGA. Means that you can configure the FPGA part, like exactly lookup tables, classes, and so on. And then you have a place to write the binary of the ARM. And then you have have an option to realize hardware-software co-design. Yeah? And both of them are configurable. Now, the typical design flow of the FPGAs, this is a bit old. I mean, I will explain this, what is the difference now to Vivado, but ISE before was like this, completely independent of this. When you want to design something, first you make a plan and a budget. Budget means that how much money you have, of course, for the production, and not only money, how much logic you need. For example, how large should be your FPGA that you want to have. And then you create the code and a schematic, and at the end you deliver some HDL, RTL design. For example, like Verilog and VHDL, and you do simulation and you are sure that everything works fine. Afterwards, you synthesize your code and you get the netlist. The synthesis process means that the behavioral level code, like the VHDL and Verilog, they are converted to a set of netlists. Means that netlist of what? Netlist of the main components of your target. For example, if it is an ASIC, then your ASIC library has AND gate, OR gate, XOR gate, and one of them has, for example, 2-input AND gate. Another library doesn't have 3-input AND gate. At most it has only 2-input AND gate. And then synthesis process means that turning this behavioral level code that you have to a netlist. A netlist is just this main components, and they are connected together. It means that actually it's a graph of the components of the library or the platform that you want, and then how they are connected together. And then for the FPGA, these components are the flip-flops, they are the lookup tables, they are the block RAMs, and DSP, blah, blah, blah. Every component which is available on the target FPGA that you have. And then you can also do a functional simulation, which is called simulation after the synthesis. And then you do the implementation. In Vivado, this is one step. It's called also implement. And in ISE, the former version of the Xilinx development tool, there was a translate, mapping, and place and route. 3 different steps. I will explain them later, what they are. And then after that, when you have implemented this, means that you just said, okay, exactly for this FPGA that I want, I know that, okay, this block RAM goes here with this configuration, this switch box should be configured like this lookup table should be configured like this, and you do completely everything is now done, and you are sure that you can build your design or put your design on that FPGA. What is important is that sometime you have some timing constraint. You want to run your design, for example, with 150 megahertz, and you set this, and then you need to check whether the timing restrictions are met. Yeah, because FPGAs are a bit also constrained compared to ASIC, because every signal cannot be easily connected to another signal. I mean, every output of a LUT cannot be connected to every other output of the LUT. Then it should pass through some switch boxes. Yeah? And then these switch boxes are active elements. They are just like gates. And then by this, they have a delay. Yeah? When they have a delay, then it's not necessarily okay to connect one signal there and to somewhere at the output of at the end of the FPGA. Then it will be a very long route, because it passes through many switch boxes, and each of them is a gate. And then the delay of this line will be very long. In ASIC, it doesn't matter. It's just it matters a bit, but it's just a wire, and the delay of the wire is much shorter than the delay of active elements like switch boxes. And then the development tools, for example, of Xilinx or FPGA vendors, they try, of course, to minimize this and do the good placement and routing to meet the timing constraint that you give. Yeah? Then usually what you do, you look at the report whether the timing constraints are met or not, and then you may do a timing simulation. Means that the result of this place and route or implement can be also simulated, considering all the delay elements which are available on the FPGA. And then if everything is fine, you generate the bit file or bit stream. This is a single file that you can configure the FPGA with, and then FPGA will work as you want. Huh? What they are, what is a translate, what is a map, what is a place and route. In the synthesis part, synthesis, as I said, it builds a netlist, but the netlist is made for every module that you have. If you build your circuit or your design with many different modules, every module will be individually turned to a netlist. Yeah? And the translate is actually merging this all netlists together and build a single netlist. And map means that to group logical entities like the gates and the endpoints into physical elements like the slices and the I/O blocks. Means that you have the netlist now. The netlist is just LUTs, flip-flop, and blah blah blah. But you don't. After the translate, you do not have any geometrical position for them. Yeah, you don't say these can be in one CLB. No, they are just LUT and flip-flops. In the map, they try to build and put them in different slices in a way that the interconnection between them is possible, because every slice has also restricted connectivity. Yeah? I mean, not every input can be connected to every other output. Yeah? And this will be done individually, and some of them will be packed together for CLBs and I/O blocks, and at the end, in the placement and route, then the FPGA tries to find place for each of these CLBs, yeah? Where I should put this, where I can put this, and then interconnection between CLBs will allow this or not. And in Vivado at the moment, all of them are done in one step, which is called implement. Good. And then at the end, you may have a look. I mean, sometimes in FPGA tools like the Vivado, you can get such a build, such a photo, such a figure that that they are the CLBs and then how they are connected. I mean, this is not much informative, but it can tell you, yeah, you have a certain line from here connected to here, or there are long routes in the circuit. Of course, if you click on them and then play with the tool, you will understand which net it is or which signal it is, and it's connected from which gate to another gate, or which LUT to another LUT, or a flip-flop, and so on. Configuring the FPGA, as I said, means putting the bit file or bit stream inside the FPGA. If you remember, I explained before that these FPGAs are SRAM based, means that they don't have any non-volatile memory. The memory is volatile, and then after the power up, nothing is inside the FPGA, and it should be configured. And then one way is to configure it directly using by a JTAG port. In some FPGAs, this JTAG port is available in the Cmod board that I will explain you. There is a USB controller. There is a USB controller which gives you also the JTAG port. Then you directly with a USB cable, like this, you can connect it to the PC. You not only are able to communicate with the FPGA that we will see today, for example, through UART communication COM port, you are also able to configure the FPGA because it gives you the JTAG port and also the COM port. In some other devices, this is not possible. There is a JTAG port here, then you need a programmer. Then you need a program which connected to the USB and the programmer to the FPGA board to configure the FPGA. And one more thing that usually in these boards, or on these boards, with the SRAM-based FPGA, there is a flash or EEPROM, which is non-volatile, and you need to configure it. And then after the power up, this configures the FPGA automatically. This is usually done by the developers of the boards which are developed as toolkit or any other device, because every device that you have, for example, you build a Cisco router, and then the Cisco router after the power up should work, you should not configure it. Then it will be configured automatically by a non-volatile memory on the chip. Now the example and the links, a Cmod A7, this is what we discussed a couple of times, what it is and how this works. And then now we get to here. This is the reference page of Digilent for Cmod A7. Again, keep in mind that there were two versions of Cmod A7, 35T or 35T and 15T. The boards that you have is 35T, and the difference between them is the size of the FPGA, and 15T is not produced anymore. But it's still, if you search, you may get it in the market, but this is just a smaller FPGA than this, but everything else is exactly the same. Just the content of the logic inside the FPGA is smaller. And this is the reference guide. Completely everything is explained, even the schematic of the board, the PCB, and everything. What is important and we have to consider together is the reference manual, if I'm not mistaken. Yes. Is the reference manual. Everything is explained. Here, for example, which FPGA you have. For example, in the Vivado project, you have to set that I have this FPGA with this packaging. Otherwise, the bit stream will not fit to this. And also, when you want to configure the FPGA, the Vivado says, hey, the bit stream that you have generated does not fit to this FPGA that I have. And what is important for you that we will see and we will talk about this is the programmable option is the quad SPI flash and also the JTAG. JTAG is, as I said, through the USB, you can easily configure it. But with the SPI flash, we need to configure the flash first, and afterwards, after the power up, the flash configures the FPGA. Then there are a lot of information about the power system, and if you are interested, of course, you read this. And about the quad SPI flash, it says how it's connected. And what is important is that it says that in some models, they integrated Micron flash, in some others Macronix. Then we have to check which board we have. I mean, all of the boards that you have should have the same flash. And then we need to define this because Xilinx provides this feature also that, for example, with Vivado, you say I have Micron and this one, and then the Vivado can configure the flash. But why they are different? Because they are connected to the FPGA in a particular way. And then the Xilinx defined this particular way. And then if you follow these instructions, then you are able to then configure the flash, which is connected to the FPGA, because you are not able to directly configure the FPGA. You are not able to directly configure the flash. First, you need to configure or the Vivado will configure the FPGA as a relay. I mean, that it relays the information or signals from the FPGA to the flash, and the flash will be configured. And then each of them should be connected to the FPGA and the PCB in a particular way. The FPGA has also the functionality with the USB and USB UART bridge. There is a chip on the board. If you look at the board later, the first chip which is connected to the USB port here is an FTDI chip. FTDI is a famous chip or famous producer for converting the USB port to many other different features. For example, UART, COM port, or either directly with some libraries you can communicate directly through the USB. But the most convenient way is to get a COM port and then using any terminal like EdgeTerm. If you have heard EdgeTerm, hyperterminal, you can communicate with the chip, or any COM port, any program that you write in a COM port, serial port. And this is the guy which not only provides the USB UART bridge, also provides the JTAG functionality to configure the FPGA. And then this is what I said, FT223, 2232 is actually the FTDI chip. Some IOs available on the chip, just 2 LEDs and another LED which tricolor LED, but we don't deal with them, and then 2 buttons, then I think button 0 and button 1, then you can push button, change them, but we rarely use this. And the analog input we don't want. There are some Cmod connector and also a lot of other connectors that you can see here on the board. As I said, this is for the breadboard. You can put it on the breadboard, and then you have a lot of input and output and analog and digital signals that you can build. You can build anything that you like almost. Good. Now let's see what I have for you. I have provided one project for you. I mean, this is also available in Moodle. It exists or it contains one VHDL file which is called Cmod A7 framework. And this is the top module. This is the module that will be on the FPGA, and the primary input, primary output of this module or entity are exactly the I/O ports of the FPGA. Anything else which is inside the module and the lower hierarchy, they are not necessarily primary input, primary output. But everything that you give here, there will be primary input, primary output. For that, you need to also say that to which pin they are connected. Because FPGA has many pins. I mean, how the Vivado should know that which pins you connected to clock, which pin is connected to, for example, UART, and any name you can give. I mean, I just called them clock, UART RX, and UART takes. With the RX, you actually receive, with takes you send, easily. Then they are connected, but you have to connect them to particular pins. How? There is a constraint file. You see constraint, and I also provided this for you, Cmod A7 master. And this is the way. It might be a bit at the moment not very easy for you to understand this, but look here, this is the way for the USB and UART. The port, which is the for example, RX is J17. How I got this J17? If you look at here again, UART bridge, as we have short listened together. here, yeah, the Rx, yeah, means that the Rx of this is the Tx of the other one, yeah. Then the Tx of the JTAG is here, J17, and then you need to say here J17, get it? From this is set property of package pin J17 to the UART Rx. And of course, you need to also identify with which voltage it works, 3.3, 2.5, 1.8, every FPGA has different options. Yeah, and then for the Rx is J18, again, is J18, as you see here. And then you need to also set the clock, yeah, and also the frequency of the clock. The frequency of the clock, why do you need to specify this? Because it's provided from the outset, again, for the timing constraint. Now, this is connected to L17, the clock, and we can see here, pin L17, yeah, and this is a 12 megahertz clock. This is a fixed clock provided from outside to the FPGA through L17, and you here get L17 and 3.3 volt, and here you define a period. And you say period is here as nanosecond. If you calculate the 12 megahertz, period is something like this. And you can say that this is the, yeah, these are the actually saved names, system clock pin. And then these are the standard form that you should add, and what do they mean is actually the duty cycle. Yeah, that for how long this is 0, for how long this is 1. Why this is important? If you give them later, at the moment we don't do it, but if you give them to PLL to multiply by something and to generate a faster clock, then you definitely need to provide them. And the rest, which is here, you can leave it as it is. They are just simple things like not looking very much at the DRC check and generate the bit stream in a compressed way to make the bit stream smaller and so on. But at the moment, don't make any concern about this. Yeah? What is important is just these three, and they are already given for you. Yeah? Means that by this framework, you can communicate through the UART, but how? Yeah, these are just the pins. You need a UART module inside your FPGA, yeah, to communicate. For that, I provided a UART module for you here with the clock, reset, data in, transmit, and receive. This UART module works single byte, means that for every single byte you need to communicate with this. You cannot configure it and say, okay, receive 10 bytes. No, it's just one single byte, and then you have to communicate with this and then receive every byte and save it in a register. Or when you want to send something, put a value at here, put a value at data in, and then say send, transmit, enable, and then wait till it says I'm actually idly. Huh? And then I have a main controller, another module as a main controller. What I want to implement, what I have implemented for you here is just like this. The UART works, you send 1 byte, you receive 1 byte, always. And then the order of the bits will be different. You say, you send, for example, 1, 1, yeah, 0, I mean in hex, check whether, yeah, you send hex 1, 1, which means 0, 0, 0, 1, 0, 0, 0, 1. Then it changes the order of the bits. It will be 1, 0, 0, 0, and 1, 0, 0, 0. Then it gives you actually 0x88. This is just this, nothing else. Then I instantiated the UART module. What is super important, the UART actually doesn't have any clock, but it has a baud rate. I mean, if you did not learn the UART communication, I would suggest you to look at least Wikipedia and understand how you can communicate with just 2 lines without any clock. Yeah, and the baud rate is important. For that, you need to set this as parameters of the UART modules. And if you see here, FPGA frequency is set to here 12 million, and also bit rate to 9,600. There are some values for the bit rate or baud rate. Yeah, there are some values, the standard values for the UART. Again, edge term, hyperterminal, if somebody learned before, here the baud rate, you can select from them. Yeah, and then you should select something which is in the list. Otherwise, you cannot really correctly communicate with the FPGA. At the moment, it's like this, 12 megahertz and 9,600. Keep in your mind that if you want to reach higher baud rate, you need also higher clock frequency. It means that you cannot have very high baud rate with 12 megahertz. Yeah? Then the error rate is very high, and then the communication will be erroneous. You need to give this value, set the constant for both of them, for UART sender and receiver. It means that it's possible to have, I mean, it's funny, but it's possible to send with one baud rate and receive in another baud rate. Yeah, but doesn't matter. We don't want to do that. Now, here I instantiated the UART module. I instantiated the FSM main controller, which resets the UART and communicate with the UART, transmit and receive. And I have also made some registers, yeah, because this value 0, this value which I sent should be stored in a register. Yeah, it will be just available for a short time through the UART. Yeah, and then this should be stored in a register and then turned, and then again stored in a register and then sent back. For that, I have a register here. Yeah, register in and another one register out. The output of the UART is written in the register if a command comes, if a signal save in is 1, and another process I have for the register out, which you can see that it actually changed the order of the register in, because everything is from 7 down to 0. Now it's from 0 to down to 7. I mean, it's not possible to easily write here register in 0 to 7. Yeah, it doesn't change the order. You have to write it like this. And it saves in the register when save out signal is 1. Then you need to look at here the main controller, what it does. I mean, I do not expect you to understand this every detail right now. No, I mean, you need to sit down and read the code very carefully to understand how this works. Yeah, but save in and save out signals are by default 0, and UART communication also by default everything is 0. And then in the reset state, I restart the UART module because it needs a reset. And then in the next one, I stay here and wait for the receive input. If the data valid, means if something came from the UART, directly at the same time, I enable the save in signal to store the value, incoming value, to a register. And I go to the process. In the process, you see just I change the order and save the output. Yeah, and the next one, everything is saved, and I need to just send it back, and I value of the back is here. Yeah, UART data is the register out, is connected to here. And then here I just say, hey, send it, and wait here until the transmit is finished. When the transmit is idly and finished, it turns back to the idly and waits for the next value which comes from the UART. Now, let's synthesize it, which may take a couple of minutes. I hope everything is clear, but of course, I mean, there are many small details that you need to check it by yourself. You need to change, for example, the code and check how it works, and then you have some imaginations, and then you need to try it. Yeah, I mean, this is something that you just learn by doing. Looking at the code of the others, the full functionally code of the others will give you some insights, but will not make you a designer. You have to design by yourself something to learn. Of course, you look at the other code of the others, I mean, this code that I have written, and then you say, if I change it, like if I write my code like this, it will work, that it will help you. But if you just look at this and change something, this may work, but will not give you this option to become a designer by yourself. Okay, and during this time, I explain you the H term. Is H term clear? No? Okay, hyperterminal. Any other terminal you have used? No? Okay, you can. Yeah, but if you can use any terminal, yeah. I mean, but H term is a small, tiny program which doesn't need any installation, and then it covers many different baud rates and so on, and then you can easily use it. But if you don't have it, just search on internet for H term, you find it. Yeah. Now it says successfully synthesized and a run implementation. Yes, you can say do the implementation. Then afterwards it does. You say synthesis complete. It tries to initialize the design and then do the synthesis. And here, for example, I can clear everything. You should keep in your mind that if you open the H term by default, you have to set the configuration. Yeah? For example, you need to have to set the COM port. Yeah? It might be the case that you don't know what the COM port you have, but of course, if you open the H term and get the list, I mean, in this case, my laptop doesn't have any other COM port, and the only one is actually not this. It has one COM port. It's not connected, then the COM port 11 that you see here is not of this port. Then we need to change it, and you will see that you get another COM port here. Or you look at, for example, the device manager of Windows, and you identify which COM port your board has. I mean, you go to the device manager, you disconnect it, you see one COM port is gone, and you connect it, and then one COM port is showing up. And then, of course, the number of COM port you can change on your computer. It's doing the optimize the design, get it out, and I connect now for the first time this COM7. And here, this R you see is a refresh. I refresh here, and you see I got the COM13. Yeah, this is the COM port which is of this port. And it's doing the root design. What I wanted to say, baud rate, you should set it to 9600 and data bits to 8 and a stop bit 1. Again, if you don't know what they are, please make yourself familiar with UART communication. And parity should be none. No? None parity means no parity is sent. And also not this CTS flow control. Yeah, this is for handshaking, and this doesn't, I mean, we do not support here. And then for simplicity, you can say I want to show everything with ASCII or hex or something like this. And this says that the implementation is done. Now you come here and you generate the bit stream. Yeah, you generate the bit stream. Again, okay. And we were here. For simplicity, we just say show everything by hex, and also when you transmit, also show everything by hex. Yeah, I mean, you can change any of them, in H term. The value that is sent here or shown here will be in which format. The value that you type here is in which format. The value that you receive here, it will be in which format it is. Okay, it's doing the right bit stream. I can show you something now. The FPGA is not configured, it's just powered in. And then I connect to the COM port and I send something. You see, I send something, I receive nothing. Yeah, here is send. If I receive something, it should appear here and receive data. Yeah, send nothing. Yeah, because it's not configured as I want. Now, when the bitstream write is done, then we need to configure the FPGA. This is also a particular process that you should learn. And also we learn how to configure the flash. You know, how we can build a file for the flash, because the same bit stream you cannot put on the flash. You have to change the format of the bit stream to be suitable for the flash, and then put it on the flash, and then after the power up, it configures the FPGA. Good. Now it's done. All right, bit stream complete. What is important is Open Hardware Manager. You say here Open Hardware Manager, and then you see open here Hardware Manager is unconnected, and you say no hardware target is open. You have to open the target and auto connect. Now it tries to check all the ports that you have to know which FPGA is connected to here. And then it recognizes automatically that, hey, this is the Xilinx blah blah Digilent FPGA, and this is the FPGA. If it's disconnected, if it's disconnected, first of all, it recognizes this, and if you open the target, auto connect, it doesn't find anything. You see? Good. Now we connect this again, and then open target. Then you select the FPGA, which was the XC7A35T, and then you say program the device. Now you need to give the bit stream. You do not need to necessarily give the bit stream that you just configured and generated. You can give any bit stream, but by default, it opens the bit stream that is generated in this project. And then you say program, then it says it's done. The program is successful. You see here is programmed. And now we go to the edge term, because I turn it on and off. Now connect. And then I send 0, 0. You see I receive 0, 0. Now I change the order. For example, it's 1, 1. I should receive 8, 8. 0, 1. Hexadecimal, it's 8, 0. This is the invert. Now converted. I mean, just the order is changed. That's all. Now, if I reconnect this, then FPGA disconnect, connect, 0, 0, it doesn't answer me because this doesn't have that configuration. Now we want to configure the what we want to configure the flash. What you need to do, you need to first add the flash, add configuration memory device. And it says, yeah, which one? You have many different things, that the list is extremely large and it's hard to find. What you can do, what we discussed is the SPI here. Yeah, I guess it's the micron. And then we come here and we say here micron. You see 3.3 volt and you add it. Do you want to program the configuration memory? No, because I don't have the file. Here, generate memory configuration file. You select this. The type is MCS, is okay. And you say memory part. This is exactly what you need to again select. 3.3. Then the size of the memory will be specified automatically. And then the interface is important, should be 4-bit. And then you say load the bit stream, and which bit stream? Exactly the bit stream that we generated. If you don't know where it is, I just follow this. Inside the folder of your project, you go to the runs, project runs, and then implementation, and then you see this, bin and bit. We select now the bit file. Then we say where it should be saved. Inside the implement, we say flash, MCS. Okay. Now the memory generation completely successful. Now you come here, you select the bits, the flash that you have, and you say program configuration memory. It says which file, here the flash MCS, and you can say erase, then program, and then verify all of them. Yeah. Was unsuccessful, would say, but another part was selected. Then we are, actually you have to select this guy. Then we delete this, remove, and then add configuration memory, this. No, and then configure, here program, the file MCS, everything is fine, okay. The erase is done, and then program operation, yeah. Then what does it mean? If I disconnect and then connect, my program should work. Means that here, disconnect, connect, and then 0, 1, hey, it works. This is the way.